record these lectures, but usually it'll be 10 minutes in, and then I'll remember to hit the button. So I apologize if you're viewing online. Niall. Neil or Niall?
Niall.
Niall, okay. So let's remember just a few things first. For instance, limits are approximations. If I give you a sequence, a sub n, saying that the limit of a sub n is L means that as n gets big, a sub n gets close to L. And let's remember how to just say that formally. What's the definition of the limit?
Is it for all epsilon greater than 0? There exists a capital N in the natural numbers such that n, little n greater than big N implies that a sub n minus L is less than epsilon?
Yes. You didn't say the absolute value,
But
it doesn't need to be an n, right? That big N could be an R.
okay.
And then to get this definition, we just take like the ceiling, I guess.
Okay.
Maybe I'll nitpick. Say that N should be an N.
Okay.
So there's, hopefully that's all familiar. Yeah? Okay. For all epsilon bigger than 0.
But real quick, wouldn't that be this? It wouldn't have to be an n, but isn't that if there exists one in R, there would have to exist one in n as well?
Yeah. So the definition you gave me was equivalent.
Yes.
But often when you're actually writing like a proof, you'll wind up with big N. Maybe it'll be like the natural log of something.
Oh, I see.
And so I don't want to have to draw like ceiling bars on top of everything. It's the same definition. It's equivalent.
Okay.
This one gives you more flexibility.
Yeah. I see.
All right. Limits of functions. If I give you a function defined on some domain U, and maybe I should include something like C is a limit point of U. Though maybe I should ask, there's like a few notations for what I mean by limit point. If I say limit point, is it clear what I mean? Are there questions about what I mean by limit point? Okay. You might also have thought it called accumulation point. The limit as x approaches C of f of x is equal to L means so I know I'm often off-putting and intimidating in class. I try not to be, and I'm just bad at it. So no one's actually, so maybe I should just be quiet. What is the definition of the limit in this sense? Okay, now I'm going to ask a follow-up. So I know that you're about to answer, Dan. The rest of you, are you not answering just because you don't want to or because you don't think you remember the definition? Don't actually remember it?
I don't really remember.
Okay, good. Thank you for being honest. That's fine. This is why we're doing this. It'll be familiar as soon as it's written down, I hope.
Yeah.
For every, epsilon bigger than 0. So the same thing. This is going to be how close f of x is going to be to L. So the eventual end result will be absolute value of f of x minus L is less than epsilon. And now we need something that measures how close x is to C. So there should exist some delta bigger than 0 that will have the job of controlling how close x is to C, such that for all x in U, and maybe I'll make a mistake, if absolute value of x minus C is less than delta, then absolute value of f of x minus L is less than epsilon. And there's like this annoying picky thing about the definition of the limit, which I screwed up. picture is useful. What would you say this limit of this function is as x approaches 2? 2, right? The limit doesn't care what the value of the function is at that point. But let's take a look at the definition up there. I'm going to point it close to me. So 2 is an element of the domain, u is the domain of the function. Is the absolute value of 2 minus 2 less than a positive number? So that would mean that f of 2 minus the alleged limit, which is also 2, should be less than an arbitrarily small epsilon. But it is not. So you need to change this definition, the one that I wrote, so that it doesn't care what happens when x is equal to c.
So do we want to say for all x in the set u set subtraction c?
Yes. So there's one option. And that definitely does it. The reason I wrote that in red below is it's like the slightly more long-winded way of doing that. Which now hopefully that is very familiar as the definition of the limit. And finally, continuity. A function defined on some domain is continuous at a point C if, for all epsilon bigger than 0, there exists a delta bigger than 0, such that if absolute value of x minus c is less than delta, then absolute value of f of x minus f of c is less than epsilon. And that was fast, but hopefully things are coming back to everyone. Oh, maybe I'll do a quick question. How long is it since people took analysis 1? Last semester?
Yeah.
2 semesters ago?
No, wait.
More than 2 semesters ago.
Yeah.
Okay. More than that would be an unfair question to ask because I couldn't tell you what I was doing more than a year ago. So, you've proven, though, in the past lots of things involving these definitions. All right, if you want to prove some limit definition, well, how should your proof go? Well, you need to prove something for every epsilon, so you start by saying, well, let's consider an arbitrarily small epsilon. Consider any epsilon bigger than 0. You need to come up with a choice of delta. Probably your choice of delta you'll figure out at the end of your proof, and then you'll go back and write it. Consider any x in the domain, assume this, do some jiggery-pokery, prove that. So let's try to do that just to get gears going again. Let's prove a limit formula. Let us prove this. For any x in the real numbers, the limit as y approaches x of y squared minus x squared over y minus x is equal to, well, maybe you just remember what it is. Maybe there's walk to do. Yeah.
And we would factor the different squares of y squared minus x squared into y minus x minus y plus x. But then the y minus x over y minus x is going to cancel out, so we're left with y plus x.
Cool. So, that's a useful bit of scratch walk. Ooh, y plus x. And maybe I'll put something in red. This equal sign isn't totally honest.
No, because as long as y is not equal to x, then we can undefine stuff.
Which happily, we want to take the limit as y approaches x, and limit doesn't care what happens when y is equal to x, so that's fine. But we did just do that bit of algebra. And so now looking at that, as y approaches x, what does it seem like that limit ought to be as y approaches x?
2y or 2x? Or is y approaches x would be 2x?
Yes. All right, so x, from the point of view of this limit, that x is a constant. It's something that's fixed ahead of time. So this x is approaching x. It's equal to x. This y is getting close to x. So the whole thing should be getting close to 2x. And that's all like scratch walk. There's no proof there yet. But somehow, like, here is the hard walk that'll happen in the proof. So let's prove that. And somehow what you just showed me is basically a limit law argument for it. But I want to go back to base principles, just the definition, and prove this claim. So let's prove that for any x in R, this limit is equal to 2x. So, well, maybe I'll give you guys like a chance. Do you guys want to like write up a proof and then we talk about it together, or should I keep talking? Should I keep talking? Okay. Keep going. Okay. Okay. And if you wanted to write up your own proof, you probably had enough time in the meantime while I was stalling to get some good headway. So let's start by just putting the preamble stuff. I want to prove something is true for any x in the real numbers. So let's consider any x in the real numbers. I want to prove this limit statement, so I need to prove something true for an arbitrary epsilon. I'll then let delta be equal to something. This proof write-up will still be pseudo scratch walk because I don't know what delta really is yet, but I will at the end, and then I'll put it there, and then if I were being really courteous, I would rewrite this so it's well written and neat, but my standing handwriting from this height isn't good anyway. It's not been totally illegible. It's been legible enough? Okay, it will get bad at points, and just tell me when it gets too bad. Let delta be something that we'll figure out later. There's the thing I get to assume. Yeah, maybe I should consider any y in the real number line. I will assume, or let 0 be less than the absolute value of y minus x less than delta. Then I need to prove something is true about the absolute value of y squared minus x squared all over y minus x minus 2x. I need to putz around with that and show that it's less than epsilon. And now we can rely on the fact that we already had some scratch walk in advance. So, I don't know, what was the first thing that happened in that scratch walk above? Yeah, we can factor the thing. Well, maybe I'll even include the description by factoring. Next, what did we / should we do? Cancel out the y minus x, which we can do since y minus x is not 0. All right.
What does that say on the side?
By canceling, since y is not equal to x. But I mean, exactly what it says doesn't matter much, just an explanation, which you already said. All right, what do next? Yeah, and at this point, I think that I won't even put the description. All right, so I'm down to absolute value of y minus x. And remember, my eventual goal is to show that this thing is less than epsilon. So what do I know that it's less than already? All right, now it should seem really familiar. I need to figure out what choice of delta will result in that delta being less than or equal to epsilon. Sure, let's, yeah. There's a proof. You said epsilon overshoot. Dan, you were about to say something. You
I
were
was
going
going to say this epsilon.
Epsilon would walk, right? And yes, then I'd have a less than or equal to there if I did that. But I already had it less than delta. So that would have been fine. Now, it's a proper analyst's point of view to say, well, epsilon would probably be fine. But epsilon over 2 is definitely fine. So I'm not going to think about whether epsilon is fine. I'll just put epsilon over 2 and call it good. That's a perfectly healthy mindset. During some applications, it's worth not making delta any smaller than you need it to be. But we won't have any of those applications in this class. Kind of. So that felt hopefully pretty familiar, pretty good. One last question. This was the computation of a derivative, which I haven't defined yet, but you already know what the derivative is. What derivative did I just compute? Did you just compute? We just compute. Guess you can kind of cheat. What's a function whose derivative is 2x?
Oh, x squared.
Hey, now think back to your memory of like day 5 of calculus, which gets forgotten really quickly. Does that look like the derivative of x squared? Yeah, it's like the change in a function that is the squaring function. It's divided by the change in the input. This pen is, I think, not going to show up well. Nice. So, with that in mind, we are now ready to define the derivative. And maybe I'll even give away what we're going to do today. We're not going to do a whole lot. Today's supposed to be fairly light because then there's like, I don't see you again until Wednesday. All right, don't try to come to class on Monday. It's Labor Day. So we're going to give the definition of the derivative, which presumably you all remember kind of, at least. We'll prove something. We'll give the proper proof of the power rule. Kind of the proper proof of the power rule. There's going to be a cop-out. I'm going to assume that something's a natural number that doesn't need to be. And we will close with whatever time is left, proving some other basic algebraic properties of the derivative. And maybe I'll point out those two are actually homework problems. So that's everything for today, but let's actually do it now. So let's remember the definition of the derivative. So the derivative is denoted as f prime of x, as df by dx evaluated at x, at d by dx of f evaluated at x, and probably a few other notations, which, there's like that notation also.
Who would use that notation? I've never seen it before.
So that was the notation that I think Leibniz originally used. He drew a little dot on top for the derivative.
Okay.
And I think during the course of history, the dot moved to the right and became an apostrophe because that's easier for a typewriter to typeset.
Okay.
Because there's already an apostrophe button on most typewriters.
I think in the differential equations class I took, the teacher was like an engineer, And he used the dot.
Yes.
That's like.
I think
common.
engineers and differential equation specialists
Yeah.
still like the dot.
Yeah. And like double dot.
Mm-hmm. I guess that gets awkward, like, you can only draw so many dots up there,
Yeah.
but you can only draw so many apostrophes, which is why you put the little n up there. Okay, I'm getting distracted with things you already know. Let's write down the definition of the derivative. So the derivative is given by taking the limit as some input approaches the input we're interested in of the change in the outputs divided by the change in the inputs. Change in the outputs. Hopefully I have the y and x in the same order as the opposite page, but as you all know, it doesn't matter. Divided by the change in the inputs. Alternately, there's this other definition where you let some variable, which is always called h for some reason, go to 0. And then you just replace this y by x plus h, because what does it mean to be close to x? It means that you're x plus something that's small. Everyone happy enough? Nice. If the derivative exists at some point, then f is called differentiable at that input x. If f prime exists for every x in that interval, we say that f is differentiable on the interval ab. And I haven't included this in this definition. So I need to actually just filter out which ones of these pens I don't like. Sometimes you'll see added to the definition of differentiability the derivative should also be a continuous function. And that'll always be the case once we get to things like partial derivatives, Gesundheit. Because it turns out derivatives can have really bad behavior sometimes, but as long as they're continuous, some nice things happen. That's not part of the definition for now. I'll write continuity when I mean it. So let's start with something kind of light. Let's prove the power rule. So the power rule says that for any natural number n, and the function from r to r given by f of x equal to x to the n, the derivative of f at x is, well, I mean, you know what goes there. What's the derivative of x to the n? Yes, perfect. And that agrees with what's on the previous page, where we computed the derivative of x squared. And the proof is the same. It will be more annoying and harder to write if we try to write up a straight up epsilon delta proof. So instead, let's follow an argument that uses the fact that you already know a bunch of stuff about limits. Let's use limit laws to prove things about derivatives. So let's consider any x in R. And I see that I've already painted myself into a corner in terms of notation. So I need to show that the limit as h approaches 0, f of x plus h minus f of x all over h is equal to nx to the n minus 1. So let's try to do that. So instead of writing the limit everywhere, I'll just take that formula and try to write down what it is and simplify it. If you like, that's exactly what Dan suggested on the scratch block for the previous thing. You probably would have written down a proof using limit laws instead of epsilons and deltas. I imagine, maybe. So let's just write this down. So this quotient, f of x plus h minus f of x, is x plus h to the n minus x to the n all over h. And let's try to simplify that. I don't know, by using some sort of interval. Yeah.
Would it be worth it to use a binomial expansion?
I certainly see a binomial. Yeah. It's not obvious that it would be a bad idea, so let's do it and see if it was a good idea.
Okay.
Right, so oftentimes when you're doing math, you should ask yourself two questions. Can you do something and should you do something? And if you can do it and it doesn't seem like it'll be too hard, then just do it, and then you'll figure out if you should have done it. If it wasn't helpful, then you shouldn't have. So let's use the binomial expansion. So x plus h to the n is x to the n plus n choose 1, x to the n minus 1, h to the power 1, n choose 2. Yeah, okay. X to the n minus 2 h squared plus dot 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 plus h to the n minus x to the n all over h. All right, and I allege that we can now simplify by cancellation. So maybe you guys would have preferred to avoid that in just summation notation. Yeah, that would be fine. I wrote it this way for a reason though, because I can actually see the cancellation happen. Or cancels. The x to the n's cancel. And next I see that I am dividing by h.
Can't we factor out an h from everything on top now?
Yeah. And then I can cancel it.
Yeah.
So, yes, yeah. Sorry, that was a pedantic and silly thing to say. Of course you were going to cancel it, that's why you factored it out. So let's do all of that. So by canceling and doing, I guess, all of these steps, what do we get? I see n times h plus n choose 2 x to the n minus 2. Oh no, there's no h there anymore. It's been factored out and canceled. So this is one of these situations where I have drastically underestimated how much space I'm going to actually want to write the things I want to write. And it won't be the only time. Nice. So that means that the limit that I want to compute, so this failed at h equals 0. But as we know, the limit as h approaches 0 doesn't actually care what happens when h is equal to 0, which is formally stated in this proposition at the bottom of the page. So that means this limit is actually the same as the limit of that formal expression, which maybe now, no, I'm still not going to write it in summation notation. N x to the n minus 1. All right, so that's the sum we wind up with, I think. And now, I think we can use limit laws to compute this limit. As h approaches 0, what's the limit of n times x to the n minus 1?
It's not done on h, so it's the same.
Yeah. This quantity gets close to itself because it just doesn't move. N choose 2, x to the n minus 2 times h. As h gets close to 0.
Get close to 0.
It'll get close to 0. This is a constant times h. You know how to shake out a limit of things like that. In fact, all the rest of these terms, will they all have at least one h in them?
Yeah.
And then it'll be a constant times that power of h. Powers of h go to 0.
In this case, I'm trying to think, do we have to worry about our, no, okay. Sorry.
Yes, so let me try to guess what you are concerned about.
Thinking like powers of the exponent, say positive, and more than one.
Yes, okay. Okay, so you weren't concerned that it was like a series and you might add up a bunch of small things and they might not get smaller in the limit.
No.
Because it's only finite.
Yeah.
Okay. Okay, yeah, cool.
Because, well, wait. This is getting pedantic, but we assumed n was a natural number.
Mm-hmm.
What if n was 1? Now, here we would add with h to the 1 minus 1, which is h to the 0, which is 1.
Son of a diddly. Okay.
What are you saying? If n is equal to 1?
Yeah, yeah.
Okay.
N is equal to 1, then look, this last term is h to the n minus 1, which would be h to the 1 minus 1, which is 0.
Yeah.
And so we would get a problem there. Meaning that this, I believe, would tell us that.
Ooh, okay. So here is, I think, both the source and the resolution of the problem.
Yes.
So the source of the problem is that you're looking at this last term and you're seeing that, oh, that looks like it's just 1.
Yeah.
But when n is equal to 0, we have a, let's start the sum here, because these are the ones where powers of h happen.
Yeah.
So this would be -2.
Oh, yeah. That'd be, or if n was 1, that'd be -1.
Yeah, -1. So we would be summing this parameter starting at -1 and eventually going down to 0. And that seems weird, right?
Yeah.
So I think this would be much more clear if it were written in summation notation. K equals 1 up to n minus 1.
Okay.
And now we see when n is equal to 1, we have the sum from k equals 1 up to 0 is an empty sum.
Okay.
An empty sum is 0 by definition.
Okay.
So,
Well, okay.
so if you notice something like this in a proof that you're writing up, I mean, you got two options. You could do some stuff like this. So now I would have to rewrite it to actually get summation notation in there, because then you notice the issue. Or you could break it up into cases and say, well, something weird happens when n equals 1, but that's like one case. I can just do that one case separately. Oh, I'm going slower than I anticipated. That always happens. All right, so, well, we're done, though. We've proven the result. This limit is n x to the n minus 1. And so the derivative of this is n x to the n minus 1. And the proof is complete. And what was this other limit law? Well, let's actually read it and make sure it says what I say it said. So let U be a subset of R, C be a limit point of U. Suppose you have two functions defined at least on U away from C. And they satisfy that they're equal, except maybe at x equals C. Then their limits are equal. And that is what we used, I think. This function, before we did the cancellation, isn't defined at 0 when h is equal to 0. But away from h is equal to 0, it simplifies to this. So this function and that function are functions of h which satisfy that proposition, so we could apply it. Nice. Cool. So we have some time remaining. So here is what I am going to suggest we do. Let's think about just the normal derivative, well, these four derivative laws involving algebra. So if I give you a sum of two functions and ask you for the, well, what is the derivative of f plus g? What's the derivative of x squared plus x?
Isn't it just probably like f prime plus g prime?
Perfect. And I guess I have an input there, so I'll put the input there. All right, sums, the derivatives distribute over sums of differentiable functions. Yeah.
You can always break that up into f prime of x naught plus g prime of x naught as well, right?
Yep. In a sense, that's just how you define the sum of a function.
Yeah.
Yeah. The product rule. The derivative of a product is given by Right, and that's something that you all remember. The reciprocal law. What's the derivative of the reciprocal of a function? Oh,
At this point, I would just think about the quotient rule, but just let f be 1.
all right, cool. What's the quotient rule? What's the derivative of f divided by g? I guess I put the mnemonic right there. You're here for a real analysis?
So
No, you're a few minutes early. You're here for Math 317?
I'm here for not theory.
Okay, you are 10 minutes early.
Sorry. I
No.
have no classes for going.
No apologies. Do. Right, the bottom times the derivative of the top, g f prime minus high d ho f g prime divided by the square of g. And you're dividing, so you better not divide by 0, so hence the requirement that g is not 0.
then we go back to the reciprocal rule that f be 1.
Mm-hmm.
And so the derivative of the constant function of 1 is going to be 0. So we can set f prime. So f prime is 0, so the first part's knocked out. And then f is 1, so we really have negative g prime over g squared.
Cool. And, well, let's see. Oh, no, there's not actually much time. So the reason I include the reciprocal rule is the reciprocal rule is fairly easy to prove directly. And once you know the reciprocal rule, you can prove the quotient rule, because what's a quotient? Well, it's a thing times the reciprocal of the other. So once you know the reciprocal and the product rule, you can derive the quotient rule without being difficult. You can just use other laws. So, I mean, my intent was actually to now have time to for you guys to think about it and ask me questions as you walk, but there's not actually much time. So, oh, but maybe I'll say this. Immediately after this class on Fridays and Mondays, I have an office hour. So, I would encourage you all to maybe, if you have time, head up to the seminar room, which is now open. Maybe walk on these problems. I'll be in my office.
That could be cute, but I would.
Okay, well, I guess if you have another class to go to, you have another class to go to.